In this lecture, we're going to go over discrete systems consisting of springs. While the end goal of this course is to be able to develop a finite element model of a continuum, we're going to start by looking at systems that are not continuous. They're called discrete systems, so we can develop some of our approaches and gain a better understanding of the process without having to deal with messy differential equations. So the first type of system we're going to look at is actually a linear elastic spring. So the load displacement relationship for a linear elastic spring is expressed by Hooke's law, which of course is our force is equal to our spring constant times our displacement. So if I was to draw what is considered a spring element, I'm going to draw a single spring. I have one end, I have two ends. So there is a force on this end, there's a displacement on this end. My spring has some spring constant. There's a displacement on this end, and then there's a force on this end. So if we use Hooke's law, we can write an equation both at node 1 and node 2. So for node 1, our force is equal to our spring constant times our relative displacement of that node. Very similar for node 2, our force at N2 is going to be our spring constant times our relative displacement of node 2. So real quickly, some notation here. For example, when I write Fe2, this is the element number, and this is the node number. The node number can only be 1 or 2 at this point in time, and your element number is just which spring are you looking at. In this case, there's only one. So I have these two equations, and I can put them in matrix form, which gives us that our forces at our two ends are equal to our spring constant times 1 minus 1 minus 1, 1 times our nodal displacements. So what's important here also is that this form of this equation with the e's is valid for any spring element that has a linear force relationship, so all the springs that we are going to look at. It doesn't matter if I have 1 spring, 3 springs, 10 springs, 100 springs. This equation is valid for each individual spring. So we're going to work on an example if we have a system of springs. So say we want to determine the displacement of a rigid block and the forces in the spring for this system that I want to draw. So here's a wall. I have 1 spring. I have a bar that has rollers on it. I have a second spring and a third spring, and these are again attached to a wall. So I have 1 spring, 2 spring, 3 springs, where each one of these springs has its node 1 and its node 2. So what's written in red are local or element level numberings. But we also have from a global standpoint, things connect at 1, 2, 3, and 4. So the blue is global. So the difference is blue, I'm looking at the system as a whole, where things in that system connect in the grand scheme of things. Whereas with the red, I'm looking at each individual spring alone. So the first step in solving any problem for a discrete system or a continuous system is to divide the system into your global elements and global nodes, which is trying to figure out how many things are in my system and how do they connect. This is the discretization step, and when we move on to computer modeling, this is your meshing step. You're taking some system and you're approximating it with some kind of grid of elements. So next we're going to look at the force relationship for each spring on the element level. So I'm only looking at each individual spring. So for spring 1, we'd have the force in spring 1 at node 1, the force of spring 1 at node 2, which are the two ends of my spring, is equal to the spring constant of spring 1 times 1 minus 1 minus 1, 1, times the displacement of spring 1 and 1, and the displacement of spring 1 and 2. I can write the same things for each element. So for spring 2, it would be the force of spring 2 and 1, the force of spring 2 and 2 is equal to the spring constant of spring 2 times 1 minus 1 minus 1, 1, times the displacement for spring 2 and 1 and spring 2 and 2. The same can be said for spring 3, which is the force of spring 3 and 1 and the force of spring 3 and 2 is equal to the spring constant of spring 3 times 1 minus 1 minus 1, 1, times the displacement of spring 3 and 1 and displacement of spring 3 and 2. So from the local level, we have 6 equations, 2 for each one of our springs, and we have 12 unknowns, the 6 forces and 6 displacements. So at this point, we can't solve the system. What we're going to do now is look at how to get rid of some of the unknowns that we have through boundary conditions and how things are connected by examining the system on the global level. So now we're going to look at things in the big picture. So we have some connectivity if we look at the big picture, and the connectivity are really some element level boundary conditions. So they're how things are related and connected. Our primary variable in this case is our displacement, and our secondary variable is our force. So what we have to do is we have to have continuity of the primary variable. For example, you can't have two displacements. If 2 springs meet at a single point, you can't have different displacements because they're at the same place. We also have to have a balance of our secondary variables or our forces. So like we have to have a balance of our forces. If we have two forces connected, if we have 2 springs connected together, the point at which they're connected, the force has to be equal and opposite in both directions for both springs, unless an externally applied load exists. So in our case, if we were to look back at our picture, our three springs connect at global node 2, which means that the displacement of spring 1 end 2, which is the end of spring 1, which connects to global point 2, has to be equal to the displacement of spring 2 end 1, because that's the end of spring 2 that attaches to point 2, which is also equal to the displacement of spring 3 end 1. Basically, I'm saying the points at which our springs connect, their overall displacement at that point has to be the same. I'm going to scroll back up to my picture because, yet again, I forgot there's an external load P applied at point 2. So our forces at point P are that are some of our forces, so the force of spring 1 end 2 plus the force from spring 2 end 1 plus the force from spring 3 end 1 has to be equal to our applied load P. This allows us to get rid of four of our 12 unknowns. We're getting closer to be able to solving the problem. The rest are going to come from the boundary conditions of the problem itself. So if we look at the problem from a global standpoint, I still have a wall, I still have my spring, I still have my bar, I still have my second spring, I still have my third spring, I still have my wall, I still have spring 1, 2, and 3, and it still has the respective nodal ends. But from a global standpoint, I have my global displacement, my global force at point 1. I have my global displacement at point 2, my global force, and I have it at point 3, and I have it at point 4. U is displacement, F is force. So if we apply Hooke's law on the global level, we would get that our force at node 1 is equal to our spring constant times our displacement at node 1 minus our spring constant times our displacement at node 2. At node 2, we would have our force, this is node 1, this is node 2, this is node 3, is equal to our displacement at point 2 plus our displacement at point 3. And for node 4, we'd have F4 is equal to our spring constant for our third spring times our displacement at point 2 plus our spring constant times our displacement at node 4. So node 2 is the tricky one because node 2 is where everything assembles. The force at node 2 will be minus our spring 1 times our displacement at point 1 plus our spring constant times displacement at node 2 plus the spring constant of spring 2 times the relative displacement between points 2 and 3 plus the spring constant of spring 3 times the relative displacement of the two ends of spring 3, which are points 2 and points 4. So if we were to lump everything together based on our displacements, we notice that at point 2 we wind up summing all of our spring constants. At this point, again, we're going to put all of our equations into matrix form to just make them compact and employ the usefulness of linear algebra to solve the system. So in this case, we would have k1 minus k1, 0, 0, minus k1, k1, plus k2, plus k3, minus k2, minus k3, 0, minus k2, k2, 0, minus k3, 0, k3, times our displacements, is equal to our forces. So at the global level, we have 4 equations and 8 unknowns. Those are our global displacements and our global forces. So again, we really still haven't quite gotten down to how to solve the problem because we still have more unknowns than we do equations, so the system's not solvable. But really, we want to take a much closer look at this coefficient matrix, which is called your stiffness matrix, and is usually given the symbol K. Because this is really showing us how everything in our problem is related to each other and how when you run a program like SolidWorks, it actually solves for your stresses and everything. So the bulk of the course is focused on how to generate this global stiffness matrix. So we take a closer look at this matrix. We can show that for columns 1 and 2 and rows 1 and 2, so these 4 K1s are for element 1. Columns 2 and 3 and rows 2 and 3 are for element 2. That's where these 4 K2s come from. And then columns 2 and 4 and rows 2 and 4 are for element 3. That's where all of these K3s come from. This is because the way that matrix multiplication works, each column is a global node and each row is a global node. So this is node 1, 2, 3, 4, 1, 2, 3, 4. So in this position, it's node 1, so it's what's at node 1. And this one over here, it's what's connecting node 1 to node 2. And why am I saying this? It's because we are going to eventually switch into using indice notations instead of writing out the K's instead of writing out the full system of equations. The goal is for you to be able to look at a picture and be able to figure out how to build the global stiffness matrix without having to write out all of the equations. So if this was written in standard row column matrix notations, we would have K11, K12, K13, K14, Again, it's row column. And then this is our global stiffness matrix, and it's made up of the element level stiffness matrices, applying the appropriate connectivities. So each one of the values in here is related to our element level stiffness matrix, that little ke times 1 minus 1 minus 1, 1. So this is called K. There's no KE because this is just your global stiffness matrix for the entire system. Our element level stiffness matrices are called KE because, again, there's one for all the elements. And those are, again, our spring constant times 1 minus 1 minus 1, 1, which is also written as KE11, KE12, KE21, and KE22, where, for example, if I was to write K1, 1, 2, what I'm saying is go to element 1, row 1, column 2, and use that value. All right, that's how matrices work. It's a little aside on notation. We'll get back to it again in a few more problems. So we have our global system of equations, right? I'm getting a little lazy here. So we have our stiffness matrix times our displacements times we go back to our global system equations. We have our stiffness matrix K times our global displacements are equal to our global forces, where we still have 4 equations and 8 unknowns. So in order to solve the system, we have to apply our boundary conditions, or those pieces of information that we can gain from what we see in our system. Namely, in this problem, points 1, 3, and 4 are fixed. So our displacement of point 1 is equal to our displacement at point 3, which is equal to our displacement at point 4, which is equal to 0. They cannot move. We also know that the force at point 2 is equal to P, which is equal to, remember, the sum of our element level nodal forces. So we can actually condense down our system, which means we're going to cross off information that we know based on, now that we know our boundary conditions, we have 4 equations with 4 unknowns, so our system is solvable. We're going to condense down our system. So if we look at our system, we have our stiffness matrix, K1 minus K1, times, I'm going to fill in our displacements, 0, U2 is still unknown, 0, 0, is equal to our forces. We still don't know F1, we know F2 is P, we don't know F3, and we don't know F4. So what we do at this point is we condense down our system, because if you had more than one unknown, you want to be able to simply write the answer, And if you were to plug this system into MATLAB as it is, you want to be able to solve it because we need all of our unknowns on one side and all of our knowns. We need all of our unknowns on the left-hand side and all of our knowns on the right-hand side. And the way the system is right now, we have everything mixed up. So if we solve the second equation for U2, we would get U2 is equal to P divided by K1 plus K2 plus K3. After we solve for our unknown displacements, we go back and we solve for our unknown forces. F1 will be minus P times K1 divided by K1 plus K2 plus K3. And F3 will be minus P times K2 divided by K1 plus K2 plus K3. And F4 will be minus P times K3 divided by K1 plus K2 plus K3. Now that we know our unknown global forces and our unknown global displacements, we can go back and solve for our unknown local forces and our unknown local displacements. So our displacement in N1 of spring 1 is 0, and this is of course equivalent to U1. Our displacement of spring 1 N2 is equal to our displacement of spring 2 N1, which is equal to our displacement of spring 3 N1, which is equal to U2, which is equal to P over K1 plus K2 plus K3. Our force at spring 1 N1 is equal to F1, and our force of spring 2 N2 is equal to F3, and our force of spring 3 N2 is equal to F4. In our next lecture, we're going to go over different systems. So everything that we derived here works for springs and systems of springs. Now we're going to look at other types of systems that can be evaluated based on discrete laws, such as elongations of bars, torsion of bars, electrical resistors, fluid flows in pipes, heat transfer. We're going to practice these discrete systems using different governing laws, whereas the process is always the same.